In this lecture, we will continue our discussion on algorithms.
There are three other notations that we need to look at. The next one is what we call the omega notation. And here's the definition. So we say T of n is equal to omega of f of n. So notice that we use an omega symbol right here instead of an O. But we say T of n is equal to omega of f of n if there are positive constants c and n naught such that T of n is greater than or equal to c times f of n when n is greater than or equal to n naught. So this is what we mean by the omega notation. So from a notation perspective, we use a big omega symbol instead of a big O. What we're saying here is that at some point n naught and onward, if T of n is at most, not at least, but at most, a constant multiple of f of n, then T of n is equal to omega of f of n. So here, when we compare the growth rates, we're saying that the growth rate of T of n is greater than or equal to the growth rate of f of n. So remember, with big O notation, we're saying the growth rate of T of n is less than or equal to the growth rate of f of n. With omega notation, we're saying that T of n is greater than or equal to the growth rate of f of n. So here, we're saying that f of n is a lower bound on T of n instead of an upper bound. Now, the one thing I will say about this particular notation is that it's not used as much compared to the big O notation. And one of the reasons behind this is because it's actually more difficult to compute than the big O. Big O notation is not too difficult to compute. You can always put together some upper bound. It may not be a great upper bound, but you can come up with an upper bound for just about any algorithm. Coming up with a lower bound for an algorithm is a lot more difficult. We'll now take a look at the third notation. So let me give you the definition first. So we have T of n equal to, and this symbol right here, if you have not seen it before, is called theta. So T of n is equal to theta of f of n if and only if T of n is equal to O of f of n and T of n is equal to omega of f of n. Now you notice I just said O instead of big of O. Sometimes we say O of something instead of just big O. I'll try to say big O, but sometimes I might just say O. But anyway, this definition pertains to what we call the theta notation. And what we're basically saying here is if T of n is both O of f of n and omega of f of n, then we're saying if it's bounded above and bounded below by some constant multiples of f of n, then T of n is theta of f of n. Now you might be asking, how is this possible? How is it possible to be both O of f of n and omega of f of n at the same time? Well, this happens when the growth rate of T of n is equal to the growth rate of f of n. We have one more notation to take a look at. So we say that T of n is little o of f of n. So notice that we're using a lowercase o right here instead of a capital O. So we say that T of n is little o of f of n if for all positive constants c, we have some n naught where T of n is strictly less than c times f of n whenever n is greater than or equal to n naught. So this is what we call little o notation. That's why we use the little o symbol instead of the capital O or the big O. I mean, all we're just saying here is it's pretty much the same definition as big O notation, except instead of saying that T of n is less than or equal to c times f of n, it's actually that T of n is strictly less than c times f of n. So another way we can think of this is we say that T of n is little o of f of n if T of n is big O of f of n and T of n is not equal to theta of f of n. So we're just saying here that the growth rate of T of n is strictly less than the growth rate of f of n. It can never be the same. It's not possible for the two growth rates to be equal. One is strictly less than the other. Now, the thing I will say about this particular notation, out of all the ones that we've looked at, this one is very rarely used. There are some circumstances where we would see little o notation, but most of the time we're going to see big O notation instead of little o notation. Let's take a look at a couple of quick examples. So here we're going to compare n cubed and n squared. Obviously, n cubed is going to grow faster than n squared as we increase the value of n. So we can say that n squared is O of n cubed. We could also say that n cubed is omega of n squared. Here's another example. Let's say we have f of n equals n squared, and we have g of n, which is another function of n, equal 2n squared. Both of these functions have the same growth rate. They grow at the same rate. Even though one of them is twice the other, when n is really large, they're still growing in a n squared type approach. So here what we're saying is constants really don't matter. And we're going to see that later on when we look at the different notations with algorithms. So what this means is f of n is O of g of n, and f of n is also omega of g of n. And if you remember from our rules, since f of n is both O of g of n and omega of g of n, then that means f of n is theta of g of n. If we can denote the running time using theta notation, that is actually preferred, and this is because it's a tighter bound. Now, what do we mean by a tighter bound? Let me give you an example. Let's say we have f of n equal to 2n squared. Technically speaking, I can say that f of n is O of n power 4. I can say it's O of n cubed. I can say it's O of n squared. All these are correct. They're all upper bounds of 2n squared. However, if you look at these three, having f of n being O of n squared is the best answer, because if we look at the growth rates, this is the one that's closest to 2n squared. I mean, in fact, they're both n squared. We just have a constant factor of 2 in f of n. So this is the best upper bound that we would get. At least we would hope this is the best upper bound. Now, if we say that f of n is theta of n squared, this is actually even better. This is actually even tighter than saying just O of n squared, because not only does this mean that f of n is O of n squared, so not only are we bounded above by n squared, but we're also bounded below by n squared. I mean, this is as good as it's going to get. We're not going to get anything that's faster than n squared. Now, you might try to put in some constant factors, but once again, we mentioned before, constant factors are ignored when we talk about this type of notation. So we're not going to get like n or something that's less than n squared. We're not going to get n 1.5. N squared is as good as it's going to get if we can use theta notation. Now you might think, well, let's just have all the algorithms use theta notation. The problem is there's only a small number of algorithms that actually have their running times expressed in theta notation. There aren't too many. A lot of them use the big O notation. And this is just because we don't know if the current running times are the absolute best. Because I mentioned before, it's more difficult to compute the lower bound. It's more difficult to compute that omega notation. If we could figure out the lower bounds, then we would have a better idea if we can achieve a theta notation bound. But because we can't get that lower bound, we don't know if the current running times of these algorithms are the absolute best. And in fact, there are a lot of research going out right now where they're trying to improve already existing algorithms in special cases. So they're working on trying to improve those bounds. We don't have that theta notation running time just yet.